that happens, because if you turn around and look at your slides, it always stays close to your mouth, whereas this way...
Oh, yeah, that's right. I remember that.
Changes.
Right.
But we can adjust your volume back there and make sure that everything's good.
Okay, sounds good. Okay. Hello? Hello? Can you hear me? Can you hear me? Anybody? Yeah. No, you can't hear me? Hello? 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 Is this one, hello? All right, let's see. Which one's better? Is this good? How's this? Is this good? Can people in the back hear me? All right. Okay, okay, are people excited about this? Yeah. Okay, let's see. Woo! Okay, I can't talk anymore after that. I think I injured my vocal cords. Okay, what is, discrete math and probability. That's what we're teaching you. Why are we teaching this to computer scientists? Eventually, you're going to program, on these things called computers. And, before computers, there were microprocessors, but now they're big. There are lots more processing. So there's nothing really micro about it except the size of transistors. It's amazing, right? These things in your phone, you talk to Google. You give up all rights to any privacy, but I'm so annoyed the phone does this. And next week it doesn't. It does something different. It's amazing, right? So Google is figuring you out all the time. So there's lots of stuff going on with these things in your pocket and everywhere. It really is a superpower. I'm not understating how big it is, and you probably all know this, but in some sense, this is why you should be a computer scientist, because you want to be in the Marvel universe, right? Because you want to have that superpower and control over the machine. So, What are they doing? What are your super powerful programs and processors doing? Really, they're doing, in some sense, there's some level of logic and proof, right? If you just write code randomly, it doesn't really do much that's interesting. Induction, you've all done, or most of you have done 61A or something like it, and you've seen recursion. And recursion is this basic principle in computer science. It is also a mathematical principle. It is the same as this notion of induction, which we'll go through, and it allows you to build up proofs about infinite sets of objects and growing sets of objects, which is what you've already done with your recursive programs. You built a program that output correctly the answer to something on an object that is of arbitrary size. And so you were already reasoning in this way, but we're going to make you better at it. What can computers do? They work with discrete objects, and I'm motivating the title of the class. Yeah, discrete math. Okay, yay. Okay, so it has immense applications. You'll see some of them. Most of the mathematics we do, we will actually come to something that's used every day in practice. Computers learn and interact with the world. They also do that. Right, we see machine learning, data analysis. We see cars driving themselves. We see robotics. Right, all of this is happening. As I said with my phone, it seems to learn better. It learns more about me than. I like the convenience, but it's a little nerve-wracking at times. But yeah, it knows how I speak. It gets better at learning, at understanding me. It's actually amazing. And the tool for that is all probability. Really, all of it comes from stuff, in principle, we're teaching you in this class. Okay? So, there's more discussion in Note 1. You should read it. Okay, I'm not. You shouldn't call. Okay, where's Babak? Okay, so,
Hello, people. Whoa. I scared myself. My name is Babak. I'm a second-time recidivist, unlike Satish here, who's serving a life sentence with CS70. He's been doing this for so long, the department has now told him, you got to get out of here next year and take a break. I'll be around for the entire semester, but for the first half, I'll be with you during office hours and available if you need to meet with me. I'll kick in and be at the podium for the most part in the second half of the course when we reach the PT part, the pain in the torso part, probability theory of the class. And hopefully we'll have a great ride together. I want to say something on a more serious note. I know that many of you are here because it's a required class. It's our objective to make converts out of you and to make this experience as enjoyable and challenging and lovely as possible. We won't always get it right. We'll make our mistakes. It's a tough effort to manage a class this large, and not all of you are even here. So we'll count on your forgiveness when we make errors and slips, and we'll try to do the same when you do. That's about all I want to say. I don't want to take too much time in the first lecture.
You want to do the rest?
Okay. I didn't prepare the slide. So here's my speech. I did my undergrad at Caltech, and I did many years of time at MIT. I took a 2-year break. Well, it wasn't supposed to be a break. I joined the patent group of a law firm after I got my PhD. I took a totally different route. They were supposed to send me to law school and all that. And I realized the fast-paced corporate life was not for me. And when a position here opened up, I took a nice pay cut and came here, and I've never regretted it. You're much better clients than corporate clients, so I'm happy to be here. What else have you put for me? Yeah, that's my email, and 517 Corey is where I do time these days. If you want to come see me, don't come and knock randomly, because I generally, even if I'm in the office, if I don't expect somebody, I won't open the door. So send me an email, give me your time windows of availability, and I'll pick something that also works for me, and I'll be happy to meet with you. Okay? I'll hand back to the secretary.
Okay, so I've been here for a while. I was somewhere else before, and I do research in theory, algorithms in particular. I taught many different courses, CS in front of all of them, CS 70, 170, 174. It goes on for a while. I also taught pedagogy. 375 is a pedagogy course, so in that course I teach, it's basically a course to support the TAs, and I teach them about educational, not theories, because I don't understand the theories, they're too complicated, but I teach them about all the experiments that are done around education in terms of what's effective. And so if you have questions about how you might want to approach the subject a bit better, I did actually do my homework on that. I have one kid in college. I have a Cal grad. Now, the question, is it in red because I love her best? Or is it because she's the most irritating? I don't know. So, but she's a Cal grad, and, I bleed blue and gold at this point, so obviously. Okay, so I use slides, and I know for some people that's a little bit different than what you've done with other math courses. So let me explain why I've done that. I mean, part of it is we don't have blackboards, right? So that's one of the issues. So I can't really do anything else, but there's other things you could use, screens and writing, and Babank will do different things, whatever suits his style. This is why I use slides. And as students, what you should do is, just make the best of it. The professors are going to do what we do. We're going to try our best. We have our own styles. It may not fit you perfectly, but you should try to get as much as you can out of each of us. Okay, so this is why I use slides. There's lots of arguments that I think are demonstrated well by examples with explanation. They're sometimes painful to write down, and so slides can work well, right? And they work well for me. Okay? Also, I don't know that there's a value for you to see me writing. It's even painful for me to see me writing. So, and one of the big benefits of slides is you get them, right? You have them at the end. You can use the slides to guide you. There's two versions. There's one version that will come out with the big, 6 slides per thing, and it doesn't show you all the flow. And that's fine. And most students use that one, if they use them at all. But I actually think the slide version is maybe a better test. If you can give the lecture, then you're great. You'll do great. And that's what you have to do there, is see that as it unfolds, what happened in the unfold. Okay, so if you do that, I bet that's one way of studying. I never pushed that because I always felt it was a little too pushy. But some students said they did that, and they said it worked well for them. So I wanted to let you know. Okay, it's possibly too fast. These are from comments. I get we do mid-semester and in-the-semester reviews, and I read every comment. I get a lot of beer and a couple of shots, and then I read every comment. And these are kind of the things that people say, right? You read, I'm too fast, or, I read versus explain slides. These are all issues that I try to explain what's on the slide. There's not so much text, so that's what I'm doing. And there's a lack of context versus blackboards, but we don't have blackboards anyway, so it's not much of a choice here. Okay. Another issue with slides is I can go fast. Okay? And, fast is, what does fast mean? Does it mean I present more and more complicated material where everybody starts really being confused or overloaded? To some extent, maybe. This course has a reputation for being, loaded. But also, I think there's other things you can do with slides. I can explain, how I see it, without having to worry that much about the details, because the details are here. So I could tell you whatever my insights are. I could tell you some great, spectacular jokes. And that itself is a joke, because my jokes are not that great. But they do, I put them in some sense to give you a break, and, so you're relieved from, focusing. Because you really need to be focusing most of the time. Okay. One thing is the pace of all our courses is pretty fast, and students get frustrated when the lecture goes by. But in some sense, that's okay. It's just the first pass. That's not the way learning works. Learning works in those moments where you are focusing, and those moments can be in lecture. They can be when you're reading the notes. They can be when you're doing your homework or in discussion or studying. Those moments when you are completely out of yourself and just thinking about the material and how it works together. Okay, that's where the learning is going to happen. So, and that's hard. And so you'll have many opportunities and many settings to do that. Lecture is one of them. Okay. Grok. I don't know. Do people know what grok means? Many levels to understand. I think it's a word from a Heinlein. Okay. Okay. Administration. We have administration. We have midterms. We have questions. You're supposed to ask them on Piazza. We have a weekly post. Read the weekly post. If you say, Babak will forgive. We don't really. Babak says we'll forgive your mistakes. He's not. That's not true. We're not going to forgive your mistakes. Okay. We won't. If you get a question wrong on the test, that's fine. We'll just take away the points. But if you don't show up to the exam, that's a problem. So just keep up with the stuff. We don't post during the week. Administrative stuff, except unless we make a mistake. We post everything you need to know in the weekly post. You need to read it carefully. Okay? Any changes in homework deadlines, any of these things are going to be there. Okay. Okay, so let's talk about some content. Today it's fairly dry, but let's just do it. So we have 4 cards on the table. Okay, they're all about 4 people. Okay, each Alice, Bob, Charlie, and Donna. That's A, B, C, D. So the card contains a person's destination on one side and the mode of travel. They're all going somewhere. Okay, so the city is on one side. For the city they're going to is on one side, and how they got there is on the other side. So let's consider the theory. Now this is just a statement. If a person travels to Chicago, he or she flies. Okay? So it's something about their destination and their mode of travel. Right? Okay, so now say you see one side of all the cards. This is an experiment. It's a social science experiment, but this is what they do with people to see whether they can understand how to do this little puzzle. Suppose you see that Alice went to Baltimore, Bob drove, Charlie went to Chicago, and Donna flew. Okay? And now you want to see which cards do you flip to test this theory. Like we're going to be little scientists here. If a person travels to Chicago, he flies. We want to check whether that's true, that statement is true in this universe. Okay, so how do we do that? Okay, we're going to do it later. So, but this is the sort of thing we're talking about today. We're talking about logic and propositional logic, what all these kind of statements mean and how you entail them. Okay? You can maybe you can guess which ones you need to turn over, but it's sort of, this is the basics of reasoning. A famous mathematician, I think, Gowers, said this propositional logic, it's not easy for him. He has a Fields Medal. It's just stuff you need to do. It's the mechanics. So you have to get this propositional logic down to just understand. Even though I teach it every year and I do this all the time, you can stumble a little bit because it's just a little bit, it has a bunch of symbols that are not intuitive. Okay, so note 1 today, note 0 is background. Read the notes, read them carefully. This is one of these opportunities you have to really focus and get stuff in your head and understand what's going on. Okay, so we're going to talk about the language of proofs, which are these are the things we're going to talk about. Propositions. This is an outline, but it's not so interesting until you do it. Okay. Okay, so what is a proposition? It's statements that are true or false. So these are statements. These are there's a bunch of letters and words there. And each one of those sentences there, or expressions, is is a statement which we can assign, which we'd like to assign a true or false statement, a value to. Now, the first statement is square root 2 is irrational. Now the question is that statement a proposition? Yeah, because it's either true or false, right? Either square root 2 is irrational or it isn't. Okay? How about 2 plus 2 is 4? Is that a proposition? Is that a statement that's true or false? It's a proposition. Yeah, oh, by the way, that one's true. Yeah, that one's true. We'll prove that next lecture, if you haven't already seen it. So this is a proposition, and what is its value? If its value is true or false, which value does it have? Not 4, right? True. Okay? So this one, is it a proposition? Yeah, it's a proposition, and it happens to be, what's its value? Okay, and so on. This is a proposition. The 826 digit of pi is 4. Is that true or false? Yeah, it's false. Okay, so, yeah, obviously I looked it up. Johnny Depp is a good actor. Yeah, okay. So any even greater than 2 is the sum of 2 primes. Is that a proposition? Yes. And I don't know whether it's true or false. This is a Goldbach conjecture. We don't really know the answer for that one. Okay, so 4 plus 5, is that a proposition? Okay. How about x plus x? No, because it doesn't mean anything, right? Alice traveled to Chicago. Now we have to think about the world that we're talking about. We're thinking about the world of this Wavesons experiment, right? Where Alice either went to Chicago or some other place. And so in that world, either Alice went to Chicago or she didn't, right? In that world of cards that we were talking about. Okay, so in that world, that's a proposition. Okay? Yeah, she went to Baltimore. Okay? I love you. Is that a proposition? I don't know. Yeah, I don't know. It's well. So the value of a proposition is true or false, right? So for that one, it's complicated. Okay. Yeah. Okay. So now once we have propositions, these are just statements, and now you can put them together. This was all there in Wavesons experiment. I'm just trying to set it up the formulas so we could reason appropriately about that experiment, about evaluating that theory. Okay, so you put propositions together to make another, and you've probably seen these. Conjunction is and. It's P and Q. And now this is another statement, okay? And this statement has a value. If P and Q are statements, each of the value of P is either true or false, and the value of Q is either true or false. Nothing else. They can't be anything else, right? And now this conjunction produces another statement, P and Q. And now this statement is either true or false, and it's true when both P and Q are true. Otherwise, it's false. Okay? Similarly, disjunction is P or Q. We're putting together two statements, P or Q, which have a truth value of true or false. And P or Q is true when at least one of P or Q is true. Okay? Else it's false. Okay, so negation is not P, and not P is true when P is false. Okay, so we've gone with our statements, which we're representing by this variable here. P is referring to some statement that is true or false. Now, for any statement that's true or false, you can put it together into this AND formulation, and any two statements, and then you get another statement. Okay, another proposition. Okay, so not 2 plus 2 equals 4 is a proposition that is that true or false? False. Okay, what about this one? A proposition that is it's false. Okay, 2 plus 2, a proposition that is right. So these are the two statements, right? This is P in the statement about Q, P or Q, and this is Q. Okay. Okay, so let's take P equals square root 2 is rational, Q is 826 digit of pi is 2. P is false, right? It's not rational. Q is true. I guess I should tell you that. P and Q are. See, this is where it gets interesting. Now we're not putting in, now we don't have to think about the statements at all. We could ignore the original meaning completely and just look at their truth values, right? That's the value of a variable. False. That's true. Not P is, now we just look it up, right? It's not false is true. Not false is true. Yes. Okay? Okay, we can put them together. So now already this is sort of interesting because you can start writing propositional statements. For example, we could think about a world where we're deciding whether these people are riding a bus. All these people. And then we could write down a logical statement. This may be if Babak had actually gone to law school, maybe he would have taken the LSAT, and this is the kind of things they do. Okay, so either person 1 or person 2 ride the bus, and person 3 or person 4 ride the bus, or, that person 2 or person 3 ride the bus, and that either person 4 rides the bus or person 5 doesn't. Okay, it's kind of a disaster. But you can mechanically translate this into a formula. And that is what that formula says. Okay, the not at the beginning is we can't have either of the following happening. Either is indicated by the or there. Okay, neither of these things can happen. Okay? And then you can sort of work out how to translate it into this propositional formula. Okay, so now the question is, can person 3 ride the bus? Is there an assignment of true, false to this to each one of these P1 values? Is there a world that's consistent with that statement, but we can't have either of the following happening? Is there an assignment of true, false values where this propositional form evaluates the true, where P3 evaluates the true? That's the question, right? Who knows the answer? Okay, I don't know the answer. Okay, but you could ask other questions about this world. Is it possible in this world that person 3 and 4 ride the bus together? So, this is complicated, like love. It's complicated, right? It's not as complicated as love. We can actually deal with this, right? Because we can program. Okay. We could deal with this rationally? I don't know. Okay, so we need a way to keep track. When you program, you need to keep track of things. Okay, that's really the first thing you have to do. You have to organize it, see where to put things. Okay, that's the notion of programming. It's integral to the notion of programming. Okay, so a truth table is essentially you have a column for each of the variables, and then you evaluate the expression in the last column. Okay, so P and Q, I just look up the row. It says true, P is true, Q is false. We know that for P and Q to be true, they both need to be true, right? So that row will be false, and that'll be false, and that'll be false. Okay, so it's easy enough to evaluate each row based on our definition of what and means. Okay, we could do it with or. True or true is true. True or false, either one. If either P or Q are true, then the expression is the proposition is true, P or Q. So that's true, and so on. Okay. You can notice some things from the table already, right? It's commutative, right? Because the middle two rows have the same values for both P and Q and P or Q. Right? It doesn't matter whether it's P or Q or you switch the values of true and false in the inputs. Okay. Now one use for truth tables is so what we could do is we could build a big truth table from the previous slide and just evaluate the expression with the basic values of every variable plugged in, and we would eventually be able to tell whether person 3 or person 4 and person 4 can ride the bus together, right? I mean, it's a pain. We would never do it by hand, but unless you're taking the LSAT. But this is you can see that it's very organized and it will give you the correct answers. Okay. Another thing you can do is show that things are logically equivalent. And again, when I'm filling out the truth table, I'm using the definitions in the expression. Okay, there's a not, P, and Q. So what I'm going to do is I'm going to plug into P, not P or Q, this true for P and this true for Q, and then just start reducing the expression. So I plug in true for P or true for Q, and then I get a true, and then I get a not true, and then I get a false. Okay, now I plug in true for P here, I get a not P, which is false. I get to plug in true for Q, which is not Q, which is false. Then I get a false, and that's false. Okay? And I can do this, right? So the key here is in each row, the variables that are in the expression are fully specified. So I could plug in the variables and just evaluate the expression. Okay? And you could fill out, it's just mechanical. Yeah.
The example of function of how and or are distributed and not commutative.
Oh. Now commutative just means you can switch true and false and they don't make any difference. That's what I mean. Yeah, that's all I mean, yeah. Yeah, he asked the question, we'll get to distributive in a minute, but I don't think it probably implies distributive, yeah, but it's not. Okay, so you can plug in. I just evaluated all these. And what do you see about these two columns? What are these two columns? They're the same. It says for every possible set of inputs, for every input, these two expressions evaluate to the same truth value. Okay? For everyone. So that means they're logically equivalent. Okay? Does that make sense? So these expressions are logically equivalent. Okay? So, in addition, this particular expression, I didn't choose it on accident. It's called De Morgan's law for negation. If you negate an and, you distribute and flip. Right? That's what we did here. Right? We showed that this expression here, not P or Q, is the same as not P and Q. Oh, I didn't show this one. I showed this one. Okay. I showed these two are equivalent. And with the truth table, these two are also equivalent. Okay? So you can distribute the negation and flip the and or. Okay? Okay, so now let's just do something a little stupid, right? Let's think about reducing an expression without plugging in all the variables. Okay, so the question is, say I have this expression and, P and Q. And for P I plug in true. Can I write a simpler expression? That's what I'm doing here. Can I simplify this expression T and Q, not even knowing the value of Q, to just Q? Okay? Does that make sense? That way if you plug in some of the values, maybe you can clean up the expression a little bit. Okay? So, is this true? Who thinks yes? Okay. Who thinks no? Okay, so I think it's yes. Okay, so and the reason it's yes is you can look at the truth table, and you could just look at the rows where P equals true. Okay? And now you see that the column that corresponds to those rows for Q is the same as the column that corresponds to those rows for P and Q. So they're equivalent. So I didn't do anything clever. If I tried to think on my feet here, I would have messed up. Here I'm just doing something mechanical. Yeah. Yeah, it's a typo. Yeah, that would be problematic. Yeah. Yeah, sorry. He's saying, yeah, there's a typo on the slide. False is usually not true. Okay. Yeah, I need to fix that. Okay. So what about false and Q? What is false and Q? Right here in this case, if it's false and Q, you can look at here, P and Q is always false. So you can also simplify that. Okay? Does that make sense? So this is mechanical. You could have been more clever and just thought it out and argued it out, but here you can just do it mechanically. Okay? And what is T or Q? Well, everything is true with this expression, the way I have the table, but yeah, it's true. Okay, so what you do is you look at the value, you look at the rows where P is true, and you see that all those rows has P or Q being true. Okay. And what is false or Q? It should be Q, yeah. Okay, does that make sense? So you can simplify a little bit, partially. Also, and the truth table is just a mechanical way to do the simplification. Okay, so now we can prove some other properties using this simplification idea, right? So what we want to do is we want to say, is there a distributive property of and over ors? Is this true? Right? Remember in elementary school or elementary school where you did the distributive property of multiplication over addition? So this is like that. Okay? Right? So you're if it was multiplication, you're multiplying P times Q and then adding it to P times R. But here it's ands. Okay? So do we think there's a distributive property or not? Okay. Okay, so what we're going to do, now we're going to write a little proof. Okay, fairly simple proof. And what we're going to say is T and Q is equal to Q. Okay, we know that. There's no T's up there, right? Okay, but false and Q is equal to false. Okay, so what values can P take? True or false? So we could just go by cases. We can see if the expressions are the same when P is true, and we can see if the expressions work out to the same when P is false. Right? And then we can use these, once we plug in, we can then we have a hope to simplify these formulas so it becomes obvious. Okay? So here's one case, P is true. So we're going to plug in true for P on the left-hand side. And we see that T and this expression up here, the simplification, tells us we can just write the second expression. Okay? And the right-hand side, we're going to plug in T in both places where P appears, and we get T and Q, or T and R. And we know that T and Q is equal to Q, and T and R is equal to R, so we get Q or R. Now those two things on the right are the same. So in the case that P is true, both the left-hand side and the right-hand side evaluate to the same thing. Now in the case that P is false, we have on the left-hand side, we're plugging in false for P, and we get false and Q or R. And what does that work out to? False and something. False. Okay, now the right-hand side, we get false and Q or false and R, which gives us false or false, which is what? Right. Okay, so in the case that P is false, we also have that the two expressions are true, are the same. They work out to the same. They simplify to the same thing. Okay? So, now the question is this distributed? Now I just showed you that and distributes over or. Does or distribute over and? I mean, addition doesn't distribute over multiplication. But I'm just fooling you. It does. So, and again, we could do this whole proof. The simplification here is to use the or simplifications. And then you can do it by cases again with plugging in for P. Both true and false. Okay, so you also have FOIL. You remember FOIL? Who remembers FOIL? Does everybody remember FOIL? Really? You didn't have FOIL? Okay, okay. FOIL is, you really don't remember FOIL? Okay, sorry. Okay, so it just says first, outside, inside, last. So you pair out the two first elements and put them over there. I guess outside, the A and D, that's next. The B and C, and the B and D is the last. Okay. B and C is inside. First, outside, inside, last. Anyway, it just gives you all pairs from the two expressions. Okay. So do and these work? Are they true? Do the FOIL formulas work? Yeah, and how do you prove them? Well, what you do is you prove them. You just cover up, and you make A or B be just one variable again. and then you distribute it that way, and then you distribute it the other way. And they're commutative. Okay? So you can build up these simplifications. So all these expressions are equivalent, are logically equivalent. And we didn't need to use truth tables anymore. Because here, the truth tables would have been a pain, right? Because you would have 16 values. 16 values. Okay? Does that make sense? So you could build up these logical equivalences as well. Okay, so now we're going to get to the big one that we really care about is, we care about everything, but this can be a little confusing. So if P, then Q. Okay? That's what this expression means. P implies Q. So if these are true statements, so now I'm writing a list of statements that are true. And the first statement is P. The second statement is P implies Q. Right? What we can conclude is that Q must be true. Okay? So now we've done some reasoning. We figured out some statements that are true, and then we figured out another statement that's true. Okay? Q. Okay? We put together the fact that P is true, and P implies Q, and now we know that Q must be true in a world where both those first two statements are true. Those two propositions are true. Okay. So, if you stand in the rain, then you'll get wet, right? So P is stand in the rain, Q is you will get wet, right? So the statement stand in the rain, if you have both of these statements, if you stand in the rain, then you'll get wet, and you also have the statement, the proposition that you stand in the rain being true, then you can conclude you'll get wet, right? It's if a right triangle has these side lengths, then a squared plus b squared equals c squared, right? So the P is the first part here, and Q is the conclusion. Okay? What is that theorem? Everybody knows this theorem. It's Pythagoras. Pythagoras, yeah. So, okay. So here's the confusing thing about implication. Here's one thing that seems to the statement P is only false. We think of this statement as only being false if P is true and Q is false. Okay? Because if P was true, we would want Q to be true. That's what this statement is meaning. It means. It says P implies Q. If P is true, then Q is true. Okay? So now there's four possibilities. P could be true, Q could be false, P could be true, Q could be true, and so on. There's four possibilities that you could plug into this expression. Okay? Four different truth values for P and Q. The only one that doesn't work is when that evaluates to false for that implication is that P is true and Q is false. Okay, so false. If P is false, what could Q be? Should Q be false? Yeah, it doesn't have to be false. It could be either true or false. Okay? Right? It can be true or false. Okay, in particular, anything implies true. Okay, so that means when Q is true, now sort of intuitively you think, well, P must be true because P implies Q. Is P true? Not necessarily. Not necessarily. P can be true or false. Okay? So the only thing this has power in sort of concluding is this particular case. It excludes the possibility that P is true and Q is false. Okay? Okay, so if a chemical plant pollutes the river, fish die. If fish die, did the chemical plant pollute the river? Not necessarily, right? Maybe, Bubba went out there and threw some dynamite in the water. I like Bubba, by the way. That was not political. I'm sorry. I'm from Texas. Okay. So, Bubba is a good friend of mine. Sorry. Let me go on. Okay. So P implies Q, Q and Q are true. Does that mean that P is true? We just said, Right? There's the and here is talking about two statements. P implies Q, and another statement, Q. So both of these statements are true. Can we say anything about P? No, that's what we just didn't do. Okay? We showed that Q was true, and we didn't conclude that the chemical plant polluted the river. Okay? Okay. If P implies Q and P are true, does this mean that Q is true? Right. So just go slowly when you do this. I mean, this is not something that's supposed to be lightning fast. You have to think about it a little bit. Okay. Okay. If the chemical plant pollutes the river, can we conclude that fish die? Yeah, that's what that if we believe this first statement, the chemical plant pollutes the river, fish die, then if the chemical plant pollutes the river, we can conclude that fish die. Okay. Yeah, and you can mess around with this, right? This is really, if you look at this sentence here, this sentence is actually a logical statement too. What it says that P implies Q and P. If you know both of these statements are true, then you know Q is true. Okay, so it's a sort of a little self-referential. Okay? Okay, so, implication in English. We use a lot of English here. In the proofs, it'll all be in English. It won't be these symbols always. So if P then Q, that's exactly the way we normally read implication. If P is true, then Q is true. Q if P. It's just reversing the order of the English. Okay? And then P only if Q. Now, is that the same statement as P implies Q? Right? It's a little subtle. So you'll see these in theorems. We'll ask you to prove something if and only if, and you'll everybody gets a little confused here. So P only if Q. So what it's saying is P can be true only if Q is true. Okay? Now, if P is true, what must Q be? So if P is false, what must Q be? False, right? So remember, P is true, then Q must be true. So if you know that Q is false, what do you know about P? It's false. Right? So P is true only if Q is true. Okay? This suggests that P can only be true if Q is true. Because if P is true, then Q must be true. Okay? Okay, so it's if Q is false, then P must have been false. Right? If P was true, then Q would be true. So therefore you have this. So P is sufficient for Q. And that makes more sense? Yeah. Yeah. I mean, you just, I said if P is false, that implies nothing. You just used Q. Yeah, you got it. Okay. Yeah, he asked the question and I answered it, but it's okay. It was cool. Yeah, it was good interaction. Okay, so, but I don't need to share. It's just, okay, P is sufficient for Q. Means that, and that's what P implies Q. If you prove, really, what does it mean? Why do we care about these words? It says that if you prove P, then you can also conclude Q. Okay? So here's an example. If I show that n is bigger than 4, that's also showing that n is bigger than 3. Right? Showing n greater than the statement n greater than 4 is sufficient for the statement n greater than 3. Right? If I'm greater than 4, I'm definitely greater than 3. Okay? Q is necessary for P. Okay, so Q is necessary for P. It says that if P is true, Q better be true. Okay? You better have that property. So again, we could use the same example. It is necessary that n is greater than 3 for n to be greater than 4. Okay? So these are all statements you'll see throughout the class, and yeah. No. That would be if and only if. Right. Yeah. I mean, if and only if means P if Q and P only if Q. It means both of those statements. Okay? It's shorthand for both of them. Okay. Okay. So, and we'll get to it. Okay, so the truth table here is, it's only false if P is true and Q is false. So we have this truth table. Okay? So now with truth tables we can write another expression, and let's evaluate this seemingly random expression. Okay, so you get not P or Q. So not P in the first line would be false, or Q would be true. So false or true is true. And not P in the second line would make this not P expression would be false, and false or false would be what? Right. And in the other two cases you get true. So do you notice that these two columns are the same? So these are logically equivalent. Okay, so this statement, we could have written implication as not P or Q. Okay? Just another way to write it. Okay? So these are two propositional forms that are logically equivalent. It's really sometimes it's much more convenient to work with just ands and nots and ors. Okay, and we'll see an example in a moment. Okay, so the contrapositive of P implies Q is not P implies not Q. Okay, so this is a statement: if the plant pollutes, the fish die. Okay? So now what's the contrapositive of this statement? Right. You just switch the order and then you negate both of them. Okay? If the fish don't die, the plant does not pollute. Right? So I negated both statements. The one statement was fish die, the negation of it is that the fish don't die. And so on. Right? The plant pollutes. This is called the contrapositive. If you stand in the rain, you get wet. So what's a contrapositive? If you did not stand in the rain, you did not get wet. That's the contrapositive. It's not the contrapositive. So, if you did not get wet, you did not stand in the rain. Okay? So, just these are, again, as I said, Fields medalists go slow with this part of the equation. So, that's a contrapositive. Okay, so logically equivalent. Now, is P implies Q the same statement as not Q implies not P? Meaning for all truth value assignments of Q and P, they would evaluate to the same thing? Okay, they are, and let me prove it to you. So we just saw on the previous slide that P implies Q is logically equivalent to not P or Q. Right? Which is, now I'm just using commutative, right? I switched the order and I made a not for the Q and I left not P over there. Right? Does that make sense? So now, this not of this thing inside implies the thing on the right. That's what this statement says. So that's equivalent to the thing inside the parentheses implying whatever's on the right side. Okay? I'm again using this inequality. Not P or Q is equivalent to P implies Q. So I'm using not of whatever's inside this parentheses. I should have animated this. Implies whatever's on the other side of the or, which is what I'm doing here. It's just textually substituted. Okay? So now I didn't do it with the truth table. I did it with another logical equivalence. Okay? Okay, so now the converse of P implies Q is Q implies P. Okay, that's what I did. You see, if the fish die, the plant pollutes, which is a converse of this. I've just switched Q and P in the if-then statement of the original statement. Okay, so this is the converse of that statement. If you stand in the rain, you get wet. If you did not stand in the rain, you get wet. Why is that the converse? There's no nots here, right? P implies Q is Q implies P. There's no nots here. There's a bunch of nots in this one. Why is that the converse? It's logically equivalent to the converse. Right? So what I would do first is I switch it. If you get wet, you stood in the rain. And then I applied the contrapositive. So this is technically the contrapositive of the converse. Okay? Which is the converse. It's logically equivalent. Okay? So now, the converse is not logically equivalent to the statement. P implies Q is not logically equivalent to Q implies P. We saw that. If the plant pollutes, the fish die. But that doesn't necessarily, where the converse is the fish die. If the fish die, the plant pollutes. And we see that other things could cause the fish to die. Right? But you could work out the truth table as well. Okay? So sometimes we use this if and only if, and that says if P implies Q and Q applies P. If both the statement, the implication, and its converse is true, then Q and P, these two statements here, are logically equivalent. Whenever Q is true, P is true. Whenever Q is false, P is false. Okay. Okay. So now, is this a proposition? The sum from I equals 1 to n of I is equal to n times n plus 1 over 2. Is that a proposition? How about that? Is that a proposition? Yeah, that statement, the first statement is either true or false. I think it's true, but, right? Because everything is bound. You see variables there and you get a little worried. But, well, actually, this is, it may or may not depend on n. What is n? Right? There is a free variable, so I'm wrong. That's not necessarily a proposition because it depends on n, right? N is free. It's not bound here. Okay, x is sort of a free variable. This could be true or false depending on the values of x. N is even, and the sum of two primes, that's also has this free variable n. So they're not technically propositions because we can't evaluate. It depends on what n is, whether this is true or false. Or it could depend on what n is, right? N could be a cat. No, it makes no sense there. Okay? Okay, so what we do is we call them a predicate. Okay, so Q of x is even. Okay, so now the statement is either true or false depending on what x is. If I plug in a value for x, if I plug in 3, then I'll get 3 is even. And that would be a proposition, and that proposition would be false. Right? So, does that make sense? Q of x is just a variable, and what the key is when you plug in the appropriate variable into x, appropriately typed the variable into x, you get a true or false statement. Okay? So, it's the same as Boolean valued functions from 61A, right? So this is really what we do in computer science. So P of n is this statement where it has this free variable n, which is indicated in the parentheses. Okay. Now R of x is a predicate as well, where the free variable is x. G of n is a free variable. Okay. And in Wazen's experiment, in that world we had 4 values of x that could fit in this particular that could make this a proposition. Alice, Bob. There's Alice, Bob, somebody with C, and Donna, Charlie. So these are the propositions that are relevant to Wazen's experiment. Okay? Does that make sense? Either the person flew or the person went to Chicago. If you plug in Alice in there, Alice flew, or Alice went to Chicago, we know that would be false. C of Alice is false because Alice went to Baltimore. Okay. And what we had in Wazen's experiment is that C of x implies f of x. So that's sort of the theory for all x, for all the x. But if person X goes to Chicago, then person X flew. Okay? So it's sort of what we were trying to get at, but we don't have everything here. We need something else. We need to say, this theory is not really clear what it means, right? Because what is X? And, how do you bind it, right? These are not even true values until you plug in values for X. Okay? Okay, so that what you do is you use these quantifiers to bind them. So there exists an X and S of P of X means P of X is a predicate. When you plug in a value for X, it either evaluates a true or false. Right? So when you say there exists an X in S where P of X, it means there exists an X in S where P of X is true. Okay? There's some value that you can plug in from the set S where the proposition P of that value is true. Okay? Okay, there exists an X in the natural numbers where X is equal to X squared. Okay? So that's a statement. That's a proposition. And it has a quantifier in it. Okay? And, so this statement says there exists an X and N. Another way to write this statement is for every possible value for X, we can just write an OR. Right? Either 0 equals 0, or 1 equals 1, or 2 equals 4, or and so on. Right? So this is shorthand for writing this thing out. Okay? So there exists one of these statements, one of these, you just put in every value for the predicate, every possible value for the predicate. If one of them is true, then there exists X in this set of this predicate is true. Okay? Yeah, it's much, there's a joke about it. It goes on for a long time, the second expression, but, okay, so for all quantifiers, is this the other thing. It says every value of X, this statement is true. P of X. Okay? For all X, no matter what you plug in from S, P of X evaluates true. Okay. So adding 1 makes a bigger number. Okay, so now we can write that using our expression. Right? Because this has sort of a free variable. It has number. Number can take any value. Right? So this is not a proposition by itself. It is a proposition because really that proposition is saying is quantifying over all the natural numbers. So for all X in the natural numbers, X plus 1 is greater than X. Okay? Okay, the square of a number is always non-negative. How would we write that? It's for all X in N, because here we're defining numbers as the natural numbers. And we're saying that X squared is greater than or equal to 0. Okay? And again, if you plug in 1, either the statement is true or false. I think the statement is always true for the natural numbers. But, okay? Okay, so now, in general, there are these universes, right? When we quantify it for all and there exists, we're quantifying it over a particular set. So, some common sets we use, for all natural numbers n, we have this statement for the sum from I equals 1 to n of I is equal to n times n choose 2, n times n plus 1 over 2. So the universe there is the natural numbers. There's a bunch of natural numbers, the integers, positive integers, real numbers. The set for it could be any set. In our case for the Wayson's experiment, it's Alice, Bob, Charlie, and Donna. Okay. Okay. So there's a lot more universes, but you've seen most of these, and they're laid out in the note. Okay, so let's go back to Wayson's experiment. Okay, if a person travels to Chicago, he or she flies. So what we're going to do, okay, you see this. You see some statements in your universe. If you plug in, Alice went to Baltimore, Bob drove, Charlie went to Chicago, and Donna flew. Okay? So, now you can ask, here it's set up where they're on cards. So Donna, she flew, she also went somewhere, it's on the other side of the card. So you may want to know whether Donna, where she went. Right? That's one question. Do you need to know where she went to test this theory? If a person travels to Chicago, he or she flies. Do we need to know where Donna went? No, right? This is what implication means, right? It's if the thing that's implied is true, we don't need to know about its antecedent. Okay? So let's restate it using the formalism, so we don't have to be clever or confused, right? We can just sort of be very careful here. So person X went to Chicago. That's a predicate. Okay. Whether or not they went to Chicago, right? We're not using destination, we're making a true false value. Okay. Q of X is a person flew. The statement says for all X in this, in A, B, C, and D, that if the person went to Chicago, that implies they flew. Okay? So now we've just set it up in this way. So now we can just go over it and look at Alice. So P of A is false. So we see for Alice, we see that they went to Baltimore, so they didn't go to Chicago. So now we know P of A is false. So we could plug that into this implication. We see P of A, in this case, is false. Do we need to know Q of A? No, because it doesn't, Q of A could be either one. It doesn't matter, right, for this theory. Okay. Okay, so now, so P of A implies Q of A is the particular, we're looking at every statement for every value of A and making sure it's true, because it's a for all statement. So P of A implies Q of A, but P of A is false. So Q of A, no matter what it is, this statement P of A implies Q of A is true. Okay, that's what we're evaluating. We're evaluating whether P of A implies Q of A. We're not evaluating P of A or Q of A, but we're evaluating this whole statement, this implication. Okay? Q of B is false. Do we care about P of B? Okay, let's look at it. We're plugging it into the predicate, and we're thinking about this statement here. P of B implies Q of B. And we know Q of B, we know this is equivalent to the contrapositive, that not Q of B implies not P of B. Right? And that implies P of B must be false, right? Because not Q of B is true, so that implies not P of B, which says that P of B must be false, right? Not P of B is true. So P of B, or Bob, must be false. Okay? So we have to check whether, and now if we turn over the card and we see that he went to Chicago, we know this theory is false. Okay? And now if P of C is true, if we know that Charlie went to Chicago, do we need to know whether they flew or not? Right. Again, we can just do it mechanically. We can say P of C implies Q of C. P of C is true, so that implies Q of C. So we need to know whether the value of Q of C is important. Okay? It can't be true or false. It must be true, so we better check it. Q of D is true. Yeah. Do we care about P of D? No. Okay, let's see why. Okay, so P of D implies Q of D. Here this is true, and therefore we don't care about this. This could be either true or false, so we don't need to look at its value. Okay? So you only have to turn over cards for Bob and Charlie. Okay? So maybe some of you figured this out earlier, but all this setup makes it so that it's just mechanical. Okay? Okay. More. Are my TAs here? No. Oh, okay. They're here. Okay. Well, let's see. Let me just see how I'm doing on that. Okay. Okay. So, okay. So, okay. Okay. So, I'm just going to show you some more examples for all quantifiers for a bit, and then we're going to talk about negation of them. Okay? Doubling a number always makes it larger. So think about it for a second. How would you do it? For all n in the natural numbers, 2 times x is greater than x, maybe? Okay, right? Okay, so that happens to be false for 0, right? Okay, you can fix this statement is greater than or equal to x, right? That one's true. The square of any natural number greater than 5 is greater than 25. How would you write that using quantification? Okay? For all x and n, yeah, you can. Here we use the implication. So here you could have done something different. What you could have done is you could have changed the set. You can make a definition for a set of all the numbers greater than 5, and just used for all x in that set that x squared is greater than 25. Okay? But, or you can use implication. You can put conditions on the set inside of the propositional statement. So we do either, you could do either. Okay? Okay, so often when we make statements, we might, if it's clear from context, if it's about numbers, we just may not use the for all, or they're just... Okay. There is a natural number that is the square of every natural number. Okay? So it's a little hard to parse. So it says there is a natural number y, such that for all x in n, y equals x squared. Okay. Is this one true? Is this statement true? There's one number y that's the square of every other number. Is that true? Okay. Okay. So let's just switch the order of quantifiers here. Okay? So this statement is false, right? There's not one number that's the square of every other number, right? The square of every natural number is a natural number. So now that's just the same statement where the quantifier is switched. For all x and n, there exists a y in n such that y equals x squared. Alright? And this one is true. And what I've done is, the predicate is exactly the same. Y equals x squared in both of these cases. All I've done is switch the order of quantifiers. So you can't switch the order of quantifiers. It doesn't leave the statement the same. Right? It changes the truth value in some cases. Right? These are not logically equivalent to switch quantifiers. Okay? Okay, so now, finally we're going to talk about negation. We saw that when we did the negation of P or Q, you get not P and not Q. What happens here? In English, what does it say? Wait. It says it's not true that for every x in S, P of x is true. Okay? It's not true that for every x in S, P of x is true. Okay? So that means there must be some x in S where P of x is false. Right? If P of x had held for everyone, this negation would not be true. Right? So it says there is an x in S where P of x does not hold. Okay? So it says this statement over here with this quantifier is the same statement as saying there exists an x in S where P of x is not true. Okay? So what we're saying is if you have a for all statement and it's not true, that means there's somewhere it's not true. There exists a place where it's not true. Okay? So you just pull it, you pull the negation inside and you switch the quantifier. Okay. Okay, what we do is we consider claims, right? This is exactly what we try to do. We try to say for all x, for all x, P of x. We're trying to prove theorems, okay? For every input, my program works, right? P of x could be my program works on this input. Okay, that's what we want to prove. For all inputs, the program works. And if it's false, what does that mean for your program? What are you doing? There's an X where it doesn't work. What are you really doing? You're being a TA. You're writing the autograder, right? you've proven to somebody their program doesn't work by catching them in a bug. So that's called a counterexample. It's called a test case that you fail on, right? Okay, so that's what, if you want to prove this claim is false, all you need to find is one element where it's not true. Okay, for true to prove the claim, this seems hard, right? I mean, it seems really easy for me to tell, in some cases, if I look at your program, I can tell if it's false. I can say, oh, look, 2 plus 2 is not 4, you're printing 3, is 4, and you're printing 3, right? And so that's a problem, right? But in other case, I look at your program and I want to prove it's good for every input. And that's much more challenging, right? That seems hard, and that's what we're going to try to build up here in this course. Okay, but before we go, okay, so the negation works in the other way too. If it's not true that there exists a counterexample, if there's no counterexample for your program, it means it must work for every input. Okay, so I'm going to introduce the people who are going to help you through the course, or I'm not going to introduce them; they're going to introduce themselves. I'm going to introduce them, and they'll introduce it. But you should get familiar with them. They're super helpful, and they are your point of contact for the course. Okay, so first is Edward M., and he is he orders the food for our staff meetings, so we like him a lot. So I'll let him introduce the next people. Okay.
What are we doing?
Just introduce everybody.
Oh, okay. This is Jerry. She's one of the head TAs.
You could tell them when your section is if you want.
Edward and I teach the CS Scholar section. This is James Gao. We have 2 Jameses.
Your name's
Evening.
Hi, this is Yining, and yeah.
I don't know your name. This is Hermish.
Hi, this is Kareet. We took 70 together, so that was fun.
Hey, this is Andrew. Just met him recently. Yeah.
This is Jonathan. He's one of the head TAs.
Hi, I'm Jonathan. I think we're supposed to be saying our section in office hours, but like somewhere in there it got lost. So my section is today, 5 to 6 p.m., somewhere in Donnell. You can look it up. But yeah, anyways. Also, I have office hours on Monday. And that's Zhao. He's awesome. Yeah. We're friends since Calso.
Hey everyone, I'm Zhao. My discussion is Wednesday, Friday, 4 to 5. Please join me in having fun. Next up is Kevin.
Hi, I'm Kevin. My discussion is right after lecture, so feel free to come. After me is Yunzhi, and she also goes by Claire.
Hi, call me Claire. My session is Wednesday, Friday, 2 to 3, and after me is Cleo.
Hi, I'm Khalil. My section is 9 to 10 a.m. Wednesdays and Fridays, and after me is Iman.
Hi, my name's Iman. My sections are Tuesday, Thursdays, 3 to 4. My office hours are Thursday, 4 to 5. And next up is Pravin.
Hi everyone, my name is Pravin Ravi Shankar. My section is on Wednesday and Friday from 11 a.m. to 12. So like the day after lecture, but hopefully it's a good time. Next I'd like to introduce Asli. I think her section is on Wednesday and Friday at 1 to 2.
Hello, this is James. He's one of the head TAs. I'm a TA, but I would also go to his section as a TA.
Or not at all. Right?
Right, yeah. So my sections are right after this in Latimer, assuming you actually can find that building, which, next up is Ryan.
Hi, I'm Ryan. My sections are Wednesday, Friday, 3 to 4, and this is Jeffrey.
Hi guys, I'm Jeffrey. My sections are Wednesday, Friday, 4 to 5, and this is Ani.
Hello, I'm Ani. My sections are Wednesday, Friday, 1 to 2, and we will have cookies. This is Jonathan.
Hi, my section's Tuesday, Thursday, 4 to 5 in Barrows. Office hour 10 to 12 Friday. This is Christina.
Hi, I'm Christina, and my office hours are Wednesday, Friday from 12 to 1 in Latimer. Yeah.
All right, well, see you Thursday. And, yes, see you Thursday. Yeah.